Let's start with the direct pollutants. Lead used to be added to gasoline to improve combustion in automotive engines. It reduced pre-ignition of the air-fuel mixture called NOx. However, lead is a potent neurotoxin. Lead emissions from gasoline reduced the IQ of children growing up in polluted cities. This was no minor effect. Lead levels were high enough in the 1970s to reduce the average IQ of Americans who grew up then by 5 points. Lead pollution has been greatly reduced due to stringent regulations that banned its use in gasoline and restricted use elsewhere across the economy. The average lead levels in Americans' blood has gone down by more than a factor of 10. This is one of the many examples where environmental regulations have greatly improved human welfare and have had a positive economic benefit that greatly exceeded the direct cost of imposing the regulation. Next, nitrogen oxides. Our atmosphere is mostly diatomic nitrogen, which is inert. NOx and other forms of reactive nitrogen are formed by breaking the nitrogen bonds, as can happen in a combustion process where oxygen reacts with atmospheric nitrogen at high temperatures and pressures. NOx emissions can be reduced by altering the combustion process or by cleaning up the gases afterwards to remove the NOx. Modern cars do both. They subtly adjust the combustion inside the piston to reduce NOx formation, and they use a catalytic converter to change NOx back into regular diatomic nitrogen. Environmental regulations have driven the widespread adoption of NOx-reducing technology, which has succeeded in reducing total NOx emissions even as energy use has gone up. But the success is less dramatic than for lead, perhaps because there are an enormous number of different kinds of NOx emission sources, and the cost of controls is relatively high. The US has reduced overall NOx emissions by about 40% since 1980. Sulfur oxides differ from lead and NOx in that they come from sulfur contained in the fossil fuels as they are produced. Coal, gas, and oil all contain significant amounts of sulfur when they are extracted from the ground, where significant can mean about 1% or more sulfur by weight. The sulfur contained in these fuels is emitted to the atmosphere as sulfur oxides, SOx, when the fuels are burned. SOx converts to sulfuric acid in the atmosphere with obvious negative consequences for human health, for buildings, and for natural ecosystems damaged by acidic rain. Sulfur emissions can be controlled by removing it from the fuel before it's sent to the consumer and/or by using cleanup technology, often called a scrubber. Scrubbers for removing sulfur typically work by using a base like calcium and then making a waste product like calcium sulfate, which in some cases is sold as a wallboard in a clever piece of industrial ecology. In the United States, typical SOx concentrations have been reduced by roughly a factor of 5 since 1980. Other rich industrial economies have also achieved deep reductions. Even China now has strong enough emissions controls that their sulfur emissions have begun to decline in the last few years, even while energy use has skyrocketed. The difference between sources of NOx, mostly nitrogen from the air, and SOx, sulfur from the fuel, has important implications for control. If sulfur is removed from fuels, for example at the refinery, one can be sure that the final users of those fuels, drivers of cars or trucks, will not be emitting any sulfur. One cannot say the same about NOx, as the amount of NOx emitted depends on details of the control technology in the individual vehicle, for example on how well a car's catalytic converter is working. Even a hydrogen combustion engine would still produce NOx, even though the fuel has no nitrogen or carbon. The fact that control of NOx depends on the operation of a myriad of post-combustion control devices makes regulation and enforcement harder. The final direct pollutant, carbon monoxide, is a product of incomplete combustion. It is made when fuels are burned without quite enough oxygen. As with NOx, its production can be reduced by altering the combustion process, and it can be reduced by catalytic converters located after the combustion source that oxidize carbon monoxide back to carbon dioxide. Since 1980, the US has reduced carbon monoxide concentrations by roughly a factor of 6.